Alright guys, promised you previously that I would do like the Faraday dynamo. I've got that over here off camera. First thing I wanted to show you, this was a Dremel rotary tool, okay, before it burned up, but I found it still useful as a demonstration of an induction motor. So that's this inner core that I have here, okay. And I've got the two parts to the, and see, you can see where it burned up a little bit. I've got the two parts to the induction motor. So the outer part of the induction motor, that's this one here. Okay, let me move the inner part out of the way for a second. And you can see, I'm not sure if you can make out that detail there. Those are laminated iron rings, right? So those are laminated sections. And then I've got two coils of wire, of copper wire. One coil over here, and then one coil over here. So as this thing is powered up, if we power it up with AC, this will take on the North Pole, and then these two quadrants will be North Pole, okay, through here and here. And then these two quadrants over here, these two laminations will start to act like a South Pole. So we'll have a magnet that is pointing, a magnetic field pointing this direction, okay? But then if we change the direction of the current, then those poles reverse, and then the magnetic field starts changing to this direction. And as we cycle and change the amount of current and reduce the current over here and increase the current over here and change its direction, the effect is if the magnetic field rotates through the stator, okay, as we supply it with AC power and vary the power in this coil until we reverse its direction, and then strengthen the power in this coil, reversing its direction. So as we keep doing that 60 times a second, 60 hertz in the United States electrical grid, just like we saw in the video, what ends up happening is we start creating a rotating magnetic field through the stator, and that's very useful when we get to this structure, which is the rotor. And again, we have coils of wire and laminated iron discs. So each one of these starts to build a magnetic field in response to the magnetic field generated by the stator. And then as soon as that current forms in the rotor through the loops of wire and starts building its own magnetic field, it wants to align itself. Remember, when we talked about magnetism, the domains want to align so that their north poles are pointing in the same direction. Well, the problem is the stator keeps changing the direction of the North Pole. So the rotor, in order to try to keep aligning, starts spinning and keeps spinning, constantly chasing the rotating magnetic field of the stator, okay? In doing so, if we connect it to an axle or a stylus or some kind of gear, we can utilize that rotational motion. Everyone has heard of a Dremel rotary tool. It's used for sanding and polishing and removing paint and fine detail work where you are using a rotational energy to grind or burr or polish or do something with whatever project you happen to be working on. That rotational motion is created by the rotor trying to align its magnetic field with the rotating magnetic field of the stator. So there we have a rotor stator assembly and a practical application of a rotor stator assembly. So let me transition now to my demonstration of a Faraday dynamo. This was gifted to me by a student about 3 years ago. So Michael Faraday, when he ran his experiment, he just had iron. His first experiment, he had a crude transformer. He had a coil on this side and a second coil on this side, and he started putting power through or conducting electricity through this coil, and he exhibited an additional current in a secondary coil. Well, we've changed that a little bit. What we're going to do is, now we've got coils. What we've got here is basically an electromagnet, or an electromagnet type scenario where we got coils of wire around a iron bar. So there's a coil over, there's one coil here and another coil there. Okay? And this coil is wound, if this one's wound clockwise, this one's wound counterclockwise. And then what we have here is called a commutator ring, and it makes contacts. I'm not sure if you can see that. It has metal contacts with little half, see the divider right there? With little half hemispheres of copper sheet right there. So as I turn that, the one hemisphere of copper makes contact with one pole, and the other hemisphere of copper makes contact with the other pole, and they never make contact with the same hemisphere of copper. Okay? So it's as if this coil is powering one of the contacts and this other coil is powering the other contact. Okay? And then this up here is a bar magnet, and this is wrought iron. So by virtue of connecting the wrought iron to the bar magnet as such, all we have to do, Michael Faraday says, we need closed loops of wire, 90-degree orientation to the magnetic field. So this iron is now magnetized, and that's roughly a 90-degree angle in that orientation. Okay, and then we need to move the coil through the flux of the magnetic field. So if I have a magnetic field here, I've got a south pole of the magnet here and a north pole of the magnet here. All I have to do is move the coils through. There it goes. By moving the current, that's a diode there. It's only allowing the current to flow in one direction. So it usually takes me a couple times to, if I turn it this way, well, I'm pushing the electrons the wrong way through the diode. So this is a handy device for showing you how a dynamo works, but it's also a handy device to show you that the diode only allows current to flow in one direction. So by turning it this way, yes, I am pushing electrons, but then when they get to the diode says, no, we're not going to take you through that way. Try coming around the other way. So when I start spinning the other way, then the diode allows the electrons to go through, and the diode is a light emitting diode, so it gives off light as those electrons go through. Now, Faraday's law says it's got to be a changing magnetic field. What happens if I do this? And take the magnet off. Why isn't it lighting up? Because I'm not exposing the coils to a changing magnetic field. Only by rotating them at high velocity, right? Only when I really crank on this thing do I get light. What if I turn it real slow? Well, I'm not passing the coils through lines of flux fast enough to generate a current. So Faraday's law says we have to have a velocity of flux. That is, the magnetic field has to cut through the coil fairly rapidly in several lines of magnetic flux. Cutting through the coil in a short amount of time is what's going to give you the current. So when I turn the wheel more aggressively, then we get current. We get a usable amount of current that is actually powering the diode. Okay, but when I slow down that rotation, then the velocity of the flux slows down, and therefore we don't get current. If I remove the magnetic field, it doesn't matter how fast I crank, there's no changing magnetic field, therefore there's no Faraday's law of induction. I'm not inducing a current in anything because I'm not exposing the coils to a changing magnetic field. It's only when I rotate them in the presence of a magnetic field rapidly that I generate electric current. Okay? Hopefully this allows you to understand Faraday's law of induction just a little bit better. Okay? That's all I got for you guys. I will add more physics content on Monday.